welcome and thank you for joining us for yet another interesting conversation series where we bring together people doing really exciting work at the intersection of learning, data, and from a very human-centered perspective. Chloe, can you fix the scribbles that are happening on the screen, please? So we are NYU-LEARN, and we are building the future of data-informed teaching and learning research here at NYU and now with our community around the world. We've got an exciting session today on understanding learners through data in computer science education. Just a couple things about NYU-LEARN. As I mentioned, we're the Learning Analytics Research Network. If you want to learn more about the projects that we've got on the go and coming up in the future, you can visit our website. We're doing exciting work looking at student successful progressions, as well as some new work focused on equity in learning analytics. As I mentioned, we're planning for the spring 2023 conversations and would love to hear from you. What are key emerging areas of learning analytics that you would like to hear people speak on? They could be new approaches, learning context, applications of data. The sky really is the limit. You can follow that link, and Chloe will drop it into the chat as well for our LA wish list. And now, without further ado, I'm going to hand this over to Kayla DesPortes, who is going to introduce our speakers and our topic for today. Thank you.
Hey, everybody. Welcome. I'm really excited to be here with both Mike and Matt. I want to thank you all for coming and sharing your time and your work with us. And so today we're going to talk about CS education. I don't know, Alyssa, if you want to stop the music or if we should stop the music. There we go. Is that easier to hear? Yeah, so I'm really excited because we're going to talk about CS education today. And one of the reasons why I'm excited about this is that in a lot of ways, we're still at the beginning of learning how to teach about CS very well. And additionally, it's a field that's always changing based on kind of different innovations in the computing space and what computing technology can look like, which I think makes for a particularly interesting conversation about how data kind of feeds into our understanding of how do we teach this and how do we understand how learners are kind of going through these spaces. So today we're going to get to see some work from Dr. Matt Davidson, who brings together his psychometric CS education and log data analysis methods to study how to measure students learning CS. He's currently an AI and ML resident at Apple, doing work over there in Seattle. So he's joining from the West Coast, like some of you guys. And he's going to share about using data to conceptualize our understanding of learners and what they know, and then how this kind of feeds into our understanding about their approach and processes to developing code. And so he's bringing his background in psychometrics as well as his background in cognitive psychology with his experience as an educator. And then our second talk is going to be from Dr. Mike Lee. He is the Dorman Bloom Associate Professor of Informatics at the New Jersey Institute of Technology. And he directs the GIDGET, or the Gender Inclusive Design Game and Educational Technology Lab, which designs, creates, and tests tech-focused educational tools for all. So he's going to discuss his work developing and studying learning technologies to teach about computing. And so he's bringing this kind of HCI, or human-computer interaction lens, along with the learning sciences to explore how he collects data and uses a range of different data sources in his work. And so he's looking at how data is going to feed back into system behavior to help facilitate learning experiences for students, and how it also feeds back into his research into understanding the system and how you can design to support learning. And so at the end, we'll get to have a nice discussion across kind of these two different perspectives of looking at learners and learner data. And so I'll let Matt take it away.
Thank you, Kayla. That was a delightful introduction. So I'm actually a relatively new PhD holder. So I think that actually is the first time that I've been introduced as Dr. Matt Davidson, which is very exciting for me. Okay, so I'm really excited to share with y'all today some explorations that I've done into what process data can reveal about CS students' learning. So I want to get started by just saying a little bit more about my background, because I think it has a lot to do with how I think about learners and their data. So as Kayla mentioned, I'm a former middle and high school teacher, and that really intense focus on students is a perspective that I've really tried to carry forward in my other work. And I also have an MEd in learning sciences and a PhD in educational measurement and statistics, which are both from the University of Washington. And my PhD work was focused on two big areas: applying psychometric methods to assessments in CS education. And a lot of that was in collaboration with colleagues in UW's iSchool. And the second piece was work with what we call in psychometrics, at least, to be log or process data. So I think psychometrics as a field is probably familiar to many of you. And in case it's not, I think it's a fair description to say it's the study of measurements of the mind. So how do we measure minds? Well, most of the things that we're really interested in measuring is unobservable. So as an example, somebody's fraction operations skills, like adding and subtracting fractions. So a big part of what people in my field do are develop instruments that elicit certain behaviors, and often those are with paper and pencil. And we think those behaviors we can use to infer the unobservable target. So for fraction operations, this might mean giving somebody some fraction addition and subtraction exercises, and then seeing whether they can do them correctly. And even though we're interested in something that we can't observe, we have some theory or idea that things we can observe, like how many fraction items you got right, are related to the unobservable thing that we're interested in, your fraction operations skill. Now, that idea that I just outlined, that I can make an inference about your unobservable fraction operations skill on the basis of your responses, is what we call validity. So it used to be the case with validity theory that we considered a whole instrument to be valid or validated. You had your instrument, and then you did some kind of validity study. So for example, you might invite content area experts to review your set of items and get them to say, yes, these items do require students to know about how to add and subtract fractions. And then you might compare test scores on your test to some other well-known and accepted measure of fraction scores. And then voila, you had a validated instrument. A little bit of sparkle. More recently, though, our ideas about validity have changed. No longer do we say that an instrument is valid, but instead our interpretations of scores and our uses of scores are the things that need to have validity evidence. So there's a lot of really fascinating detail that I'm going to gloss over here, but in brief, interpretations of scores are the inferences that we draw from them. So for example, that a student with a high score on our test is proficient in fraction addition and subtraction. And the use of scores is just that. So what are we going to use the scores from our test for? For something like an SAT or a GRE, the use is admission to an educational program. And so to consider those interpretations and uses valid, we have to do research, observe the behaviors, collect evidence, and then make arguments that specify a chain of reasoning connecting a student's score to the interpretation, and then connecting that interpretation to the proposed use. So what can we learn from learners? So this brings us to the big question: what can we understand from learner data? And I think that we can understand a lot of really interesting things about learners from their data, but it's limited. We're not getting a whole picture of what's going on for a learner just from the data that they generate. It also needs validity arguments. So it needs to be based on some clear reasoning and evidence about how and why the data we're collecting should be interpreted the way we're interpreting it. It also shouldn't overdetermine what we think of a learner, because we know we're not getting the whole story of that individual. And finally, but certainly not least, the data needs to have some kind of benefit to learners. You need to be thinking really deeply about whether and how data that we're collecting is benefiting the people that we're collecting it from. So now I'm going to turn to an example from a study I did a few years ago, showing what we might be able to learn about CS learners from their data. And in this study, we used Think Aloud data to try and understand the process that CS students use to solve some items. And we're focused here on response processes, which are cognitive and other processes that are involved in a student's response to an item. In general, this is a less frequently used form of validity evidence than looking at the structure of the test or having an expert review the content. And that's especially true in computer science education. Most assessments developed in this area only have validity evidence from the internal structure of the test content, or the relationship of the test with other measures. And this led us to our research question. We wanted to see how varying non-construct item features, so things that wouldn't really change fundamentally what the item is trying to measure, wanted to see how varying those would influence response processes. And our goals were to understand what sort of aspects of items we could vary, and then to see whether varying those changed the process that students engaged in to respond to the item. And so to do that, we started by developing a framework of item features. And these were features that we suspected would change what students did. And we identified 3 dimensions to think about those varying features. So the top one, cognitive demands, those are the primary cognitive process that students engage in, like reading and writing of code. Openness, one below, is the degree to which an item allows multiple possible responses or ways of solving. And evidence of thinking is what evidence we collected about students' thoughts. So for example, just asking them to explain their thinking as part of the item. Now in this presentation, I'm just going to be focusing on the writing syntax items and the openness dimension, because that's where we found the strongest evidence of an influence on students' response processes. So now I'm going to share one example item just to show the difference between what we were thinking of as an open and a closed item. So this is part of one of the writing syntax items we gave. Students were given a chunk of code, which I don't show here, and then they were just asked to write a program that'll determine if a number is prime. And so we considered this to be an open item because of this direction here, that students are just to write their code. They're not given any instructions on how to write their code other than the description of what the code's supposed to do. For the closed version on this item, the code chunk and the description are the same, but the directions are a bit different. Instead of being told simply to write their code, they are told to follow the steps below to create their code. And each step corresponds to a single line of code that we expect in the student's response. So for example, they're supposed to start with an import statement, declare a main class, create a public static method, and so on. And we considered this a closed item because we ask students to write their code in a particular way by following these step-by-step directions. And to explore these item features, we had university students studying CS do think aloud interviews. That is, we just told them to think out loud what they're saying, what's in their mind as they're solving these items. And we varied the items based on the framework that I introduced a few slides ago. We transcribed the interviews and then coded them according to the primary process that students engaged in, which gave us these 6 categories of codes over here. It's sort of different moves that students could make. So monitoring, for example, refers to metacognitive activities like realizing you don't understand something. And problem solving would be things like reading the task requirements. And we also had some more detailed codes on the right there. And I'll just be focusing on talking about writing semantics in this presentation, which were the planning and revising behaviors that students engaged in when they were writing their code. Now, to analyze this data, I used 3 techniques to try to see how the item features influence response processes. And the data that I was working with were the qualitative codes that we had applied to the transcript segments. So one of our approaches was just for each item feature to compare the proportional frequency of each process category. And these codes are also ordered in time because we got them from the transcript. So you can also treat them as a sequence of process steps. And this let us apply the next 2 methods, which is sequence dissimilarity, which is an ANOVA kind of analysis to see whether an item feature explained how similar groups of sequences are. And then finally, we used sequential pattern mining to find in a little bit more detail some subsequences that discriminated strongly between the item features. And I'll briefly introduce these 2 sequence methods and then share some results. So sequence dissimilarity analysis shows us really broad differences in sequences, but it takes the order of the steps into account. So consider 3 fictional sequences, A, B, and C here. Each of them have 4 steps. And for any pair of those, we can compute a distance by adding the lengths of both sequences and subtracting 2 times the longest common subsequence. And that gives us a single measure of how dissimilar sequences A and B are. We can then put those distances into a matrix with pairwise distances for all the sequences we're looking at, and then compute a sum of squares by squaring those pairwise distances within an item feature. So doing that, for example, for all open items. And we can also do that between features, for example, between open and closed items. And that actually allows a straightforward application of an F-test to see whether an item feature explains significant discrepancy between sequences. The other method that we use is sequential pattern mining. And that shows us a lot more detail than sequence dissimilarity. by finding subsequences that are strongly associated with a given item feature. And it starts by discovering frequent subsequences according to parameters that we set. In this case, we wanted to look at sequences that appeared in at least half of students' responses, because we wanted to try to capture general aspects of the item rather than the specific solution that 1 or 2 students used. We also wanted to set a maximum length of the subsequence to be 3 actions, just to keep it a little more interpretable. And then we applied a chi-square test for each subsequence with a contingency table like the one shown here. So for a given sequence, the table shows whether that sequence was present or absent from the open and the closed sequences. And then we construct the same table for the second subsequence that we found, and so on for all of the subsequences. So these are the results from the sequence dissimilarity analysis. It's a big ANOVA table, but we're just going to be focusing in on the openness up here. And so it showed us that for all 3 item features, we did find only for the openness and the cognitive demands do we find some significant results. But we found that openness did explain significant discrepancy in the sequences. And this result shows that not only were the sequences different, but the order of the steps were more consistent among the open items as compared to sequences as a whole. And then these are the sequential pattern mining results. Again, a lot of text on the page, but we're just going to be focusing up here. There's also a p-value and the frequency in addition to the subsequence shown there. But I really just want us to focus in on these top 5. We didn't find any significantly discriminating subsequences, but I do think there's still a lot of things that we can learn from this. These top 5 sequences all involve some combination of typing syntax, planning for a single line, and then rereading the program specification. And so all of these we saw more frequently on the open items than the closed. And that suggests that when students didn't have the line-by-line description of code to write, they engaged in a process of planning for a single line and then referring back to the specification. And so it suggests that the closed items required less checking back and forth between the specification and the student's plan as they were developing it. So looking across our 3 analytical methods, we found some strong evidence that the response process for an open item was different than that from a closed item. Overall, students did more planning on the open items, and they were more likely to plan a single line, write that line, and then check the program description than they were on the closed items. Now, these have important implications for the construct we were trying to measure, writing code. Asking students to write code is assessing more than just simply typing out syntax. But it also clearly includes a dimension of planning. So it means we might have 3 different goals for a code writing item. It might be simple translation of natural language to code. It might be planning and executing a plan for a written program, or it might be interpreting and implementing a description of a program. And that's an important finding both for assessment designers and instructors, because it has a bearing on what aspects of the construct any given item is assessing. And it's also a really important consideration for validity. A high score on an open item might be more indicative of a planning skill, while a high score on a closed item might indicate what we could call a translation skill. And looking at the response processes that students engaged in can help in making that validity argument for the interpretation of scores from those items. Now, this study was really narrowly scoped. We weren't trying to build a giant analytics pipeline or anything like that. We really just wanted to understand these specific items and what it took for students to respond to them. But that focus on the specific items and the process that students used did surface some helpful insights about code writing items more generally, which I just shared on the last slide. Now, if we had been working on an analytics pipeline, the study would have also been a great first step in doing so. The richness of the qualitative data that we collected would easily support future quantification. So for example, we might have collected some other kind of interaction data, and we might have been able to find some indicators in that interaction data that related to the process steps that we observed in the think alouds. And that would have given us a really strong foundation for a validity argument about those log indicators. And then finally, I do think that there's really exciting potential for process or log kinds of data to help us understand learners. But that work has to be grounded in an evidence-based argument about why the data should be interpreted and used in those ways. And as long as we're doing that, I think we can do some really interesting work. And I want to end with a little bit of a note of caution. So collecting this kind of data from students, whether it's a keystroke log, code snapshots, message board engagement, it all comes at a cost. And that cost is learner privacy. Now, learners give us their data, but what do they get in exchange? I think there's some ways that we can do better about this. We can think of what value an analytic might give directly to students. I think we can be transparent about exactly what we're collecting and why, and how we're going to use it to make our interpretations, just like sharing a rubric for a final project in advance or talking about how a midterm is going to be graded. We can invite students to opt in for certain kinds of collection, whether that's for a study or for a course. And then finally, I want to pose a question. What if we gave learners even more power, even more control over their data? What would it look like to let a learner curate a kind of portfolio from their data, being able to present themselves to their instructor as they want to be presented? And with that, I'd like to thank you all for listening and look forward to discussing with you all really soon.
Awesome. Thanks so much, Matt. And we'll just let Mike head right in.
Awesome. Give me a second to load up my presentation and share my screen. Okay, hello everyone, and thank you for the invitation to talk to you today. I'll be talking about some of the work I have been doing over the past few years, focusing specifically on the data we collect to help us understand our users and how we use the data to improve both the systems themselves and the user's learning experience. So hopefully you'll see from the examples that different projects can lead to very different types of data collection. I definitely agree with Matt's presentation about instruments and content validity, and I've thought about this very deeply in my work as well. But for this talk, I know we have a very general audience, so I'm planning to keep descriptions intentionally at a very high level to keep things kind of non-technical, but I'll be happy to go more in depth during our Q&A time. So first, I'll start by talking about a prototype tangible programming environment that we designed for elementary school students to make and tell stories. And this is going to be a set of examples that I have of 3 different projects that I've done to kind of show the different types of data that we collect and how that data might be used to improve the system, but also improve the learning experience. So for this project, the children worked in pairs to draw on pieces of paper, record sound effects using a microphone, and have a real robotic dinosaur named Pleo to perform actions based on touch input and physically touching the actual robot. So you can see the setup here has children. You can see the setup as the children and the researchers saw it, with a large table in the middle of the room where the children could interact with the system. So here's another pair of children using the interface and an alternate system view of the interface from the bottom. Each blank piece of paper had a unique fiducial marker on the back that the system could recognize consistently, independent of what was actually drawn on the paper. So the kids were able to draw whatever they wanted, and the system didn't actually care, but they would just kind of know with that unique ID what that image was. So the touchscreen GUI consisted of a conversation between the dinosaur and the children, where Pleo would ask the children what he should do, and then ask the child what they will do. So for example, here, the children have Pleo start the story by nodding his head. And next, when Pleo asks the children what they will do, they indicate that he should wait until they touch his head. And when they do, he should lift up his rear left leg, and so on. So they kind of build up this story. So we gave very little instruction to the young children, but they ended up making very, very complex and interesting stories and interactions. And they used variations of touch, drawings, sound effects, and actions to play out all of their stories. And the children were super engaged with the activity, and they communicated that they wanted to learn more about coding after this activity. And they also indicated that they enjoyed the opportunity to express themselves creatively in a very open system, and that it was really, really fun to watch Pleo do what they wanted to do, what they wanted him to do step by step. And they got a real kick out of Pleo really having to wait for that input. So they would wait and wait and be like, oh yeah, I remember I have to touch Pleo's head, or I have to touch Pleo's leg for him to continue with the activity. So for this very open-ended prototype project, we're able to collect several types of data, and these included physical and digital artifacts, including the children's drawings and their recorded sound effects, the actual stories that accompanied the drawings and the sound effects. We had timestamp records of the user's input into the system, so everything that they did in the system, the clicks, we had a timestamp for that. We had video recordings for the researchers to capture the user's action and oral stories. And finally, we had post semi-structured interview responses from the children, where we asked the children about their experience with the system, what they liked, what they didn't like, any questions that they had, and so on. So this was a relatively small and short study. So the use of this particular data set was pretty limited. But for the most part, we used the information that we collected to make iterative improvements to the existing features and to the user experience of this prototype. So for example, we found that the children loved recording their own sounds. So they utilized the sound effect recording feature much more than we had originally anticipated. So it was a bit buried in the original interface. So we made sure that in later versions that it was readily available and visible on the main home screen. We also found that even the small amount of text that we had in the interface was a hurdle for many of our youngest participants. So we removed nearly all of the text in our interface and replaced everything with icons and pictures, which we created together with the other young children. And from the start, participatory design was really important to us. We involved children from the beginning. So we start out with a little bit older children who could read effectively. So we got a certain kind of feedback from them, but we found that even younger children, it was obvious after the fact, was that some of the younger kids couldn't read effectively. So we had to change the interface to account for that. And finally, as with all our studies, and which is obvious to all of us researchers, we published on the work, which helped others build on our findings and design. And we've also benefited from this work tremendously because all of our subsequent work has included working with children to some degree. And so these experiences and data have been invaluable in designing effectively for young people. And I say again and again to my students that your users are never the designer, and that especially children will find ways of using your system that you would never expect. And to always kind of be ready for that. It's always very, very fun to work with young children. So next, I'll talk about another project I have called Gidget. So Gidget teaches programming concepts through debugging tasks. And the tasks are framed as puzzles within the storyline of a game where players have to help a robotic friend complete its missions. So I know that many of you may be unfamiliar with Gidget, so I'll give you a quick introduction to the features of the game and talk about some of the research that we've conducted with it. So here's a screenshot of the main game, and I believe it's covering functions. So we built Gidget from the ground up, which included making an IDE in a browser, creating a Gidget language and parser, and deploying it online. So next, I'll talk about the interface and describe some of the features we included to help players learn coding. So first, players learn programming concepts by debugging existing programs before creating their own programs. So unlike many other educational technologies where creation starts immediately using a blank slate, we wanted learners to have experience with the code before allowing them to make things from scratch, which can be much harder to do, especially without any external help. So as you can see here, broken programs are given to the player at the beginning of each level, and it's the player's job to fix it. So they see almost complete code. And to support debugging the faulty code, learners can execute it one instruction at a time to see exactly how the program runs. And here they can control the granularity of the execution as well. So they go one step at a time, or they could go one line at a time, or they can just execute the whole code all at once. And as the code executes, all the objects, state and call stacks are inspectable, so the learner can see exactly what happens as the code runs step by step. And this came from our interviews, our early interviews with many introductory students who didn't really understand the step-by-step process of how things actually work. So by allowing them to inspect these objects each step at a time, they can see how, for example, variables would change. And that really kind of opened their eyes to what was actually happening, especially in things like loops and conditionals. So here's a short clip of someone playing the first level, which is designed to be very simple to get players familiar with the game goals and its features. So you'll see here the player running her code on the left panel, and she notices that Gidget doesn't complete the goal because of some error. So Gidget is sad here, as you can see. So she goes back to edit the code so that it's correct. So you can see the code here says right originally, but the goal condition is for Gidget to be on the same position as the puppy. Now the test condition runs after executing the code, and she finds that Gidget is happy. So she completed that goal for that first level. So playing the game and solving puzzles is equivalent to debugging, which gives learners the necessary experience with the programming language to create their own program from scratch later. So we also wanted to make sure that the game was fun to play. This means that it should be appealing not only to people who want to learn programming, but it also should be fun for people who just want to play a game. And that was really important to us. So this introductory screen shows the story that sets up the theme of the game. Gidget is damaged on his way to save the animals from a chemical spill, and now he needs a player's help to fix the almost correct code to complete the missions. So next, the game frames the computers as helpful but fallible collaborators. So this is in contrast to other educational environments, which often frame the compiler, the interpreter, or the development environment as all-knowing authoritative figures. So this was really important because we found, again, through early studies, that novices lose a lot of self-confidence because they feel they aren't smart enough because they get so many error messages in the beginning. And, as experienced programmers, we know that the error messages are there to help us and that, fixing one may fix all the others. But for a beginner, seeing a whole bunch of these can be very, very discouraging. So next, each level has embedded goals, which give learners an explicit goal of debugging faulty code. So they're focused and not distracted by additional kind of objectives that can negatively affect their performance. So the goals themselves are written in the Gidget language itself, so players can get an additional exposure to looking and reading the language. Now, Gidget's missions mainly involve saving animals to make the goals more purposeful. And the game includes embedded instructions, providing learners with a sequenced set of instruction materials with specific learning objectives for each level. So more specifically, these learning objectives include everything on this list, which covers a large set of CS1 or introductory programming concepts. So now, because this is completely online and there's no teachers available, we wanted to make sure that learners could get the help they needed. So Gidget also provides information and gives examples and explanations during code execution to help learners orient themselves and move throughout the game. We include assessment levels at the end of each module to help learners mentally simulate code execution and provide them with both corrective and reinforcing feedback. Then we provided scaffold help by including help in many, many different ways, including tooltips, a glossary, and we also had a frustration detector that I'm going to talk about briefly, which looks to see if players' actions deviate from an expected average, and if it does, give them some kind of encouragement or intervention to help them get past that hump. Finally, we also stress gender inclusiveness in the design. So for example, since females make up a large proportion of gamers, but very underrepresented in computing fields, we built on best practices for being gender inclusive. So you'll notice that I've been using the gender specific pronoun he to refer to Gidget, but in the game, Gidget uses gender neutral pronouns. We also removed any violence-oriented terms, so remove instead of destroy, for example, and added socially relevant themes like cleaning up a chemical spill and helping a partner, all which have been shown to engage all gender identities. So we designed all of the game and its features over an iterative design process, including some participatory design by different stakeholders and our target demographic. So we've conducted numerous studies using Gidget over the years, mostly as controlled experiments. I'm just going over them very, very briefly here. So bear with me. So first, we have a study examining how character agency and shifting blame about errors to the computer affects people's engagement. So we have, you gave more traditional error messages with a terminal screen and another condition where the computer had a face and emotions and used pronouns to deflect blame and put blame on itself instead of the player. And we found with this simple manipulation, people would actually play much longer and complete more levels. Similarly, we had a question about whether the objects people interacted with would matter, saving blocks versus saving bugs for saving animals. And we found that those playing with animals and saving animals actually perform much better, were more engaged, and completed more levels. We also examined how explicitly testing players throughout the game with obvious exam levels might affect their engagement. We found that those playing with exam levels, as opposed to those without, completed more levels and actually reported liking the exam levels because they are more helpful. And finally, the last example I have here compared learning outcomes from several different coding learning resources. We compared Gidget the game the Code Academy Python tutorial, and the Digit Puzzle Designer, which is kind of like Scratch, where you have an open slate and no instruction. You can kind of build stuff. And we found that those playing Gidget the game and Code Academy showed significant learning gains in a post-test, whereas those playing Gidget the Puzzle Designer showed no learning improvements. Okay, so what data have we collected with Gidget? Well, as you can imagine, we collected lots of automated data, and this includes code edits, and this is at the character level, including deletions, cut and paste events. They're all timestamped, so we essentially have everyone's entire code history for each level that we can play back. We have code executions, so we can see how many times someone ran their code, the state of the program when it happened, and all those different kinds of things. Mouse activities and events, interface activities and events, and miscellaneous elements such as how many levels a player completed and how long it took them. And for all the studies that I mentioned earlier, we also collected survey data that was specifically tailored to that project. So there's tons of things we can do with this automated data that we collect, especially when we have hundreds of thousands of players' activity and code information. So for the most part, we use the information that we received to make iterative improvements to the game performance, store into the curricula. So these are very macro-facing changes that affect all of our users. So for example, early in the process, we found that many players were spending a long time on one level, and for those that passed, they finished the next level very, very quickly. So we tried swapping the order, and we found that overall, doing this improved overall completion rates, and the time to complete levels became much more comparable with each other. Another example is that our logs indicated that learners were opening up tooltips and closing them almost immediately, meaning that it probably wasn't intentional. So we found that by adding a half-second delay to the tooltip deploying, it didn't cause these quick closures and actually increased the time spent on tooltips in cases where the player did open it up. We also can make much more subtle changes based on our findings. So for example, we designed a relatively dumb coarse-grained frustration detector that simply took the mean value of certain actions from the entirety of the data set. And if a player was 2 standard deviations away from that value, the system would provide an intervention, for example, giving them encouragement, giving them hints, and or providing them extra levels for extra practice. And that's actually a good segue into our next and final example. And the last project I want to talk about is our research activities focused on trying to increase diversity in computing by working with local underserved and underprivileged youth. So I have a lot of photos here to show, but I blurred out the kids' faces since I believe this presentation will be shared publicly. So we've run many summer camps, one-day coding sessions, and after-school programs using our tools and other resources. And most recently, our main focus has been increasing participation and diversity in computing in the Newark area. So we established partnerships with the Urban League of Essex County and Newark Public Schools to run the Newark Kids Code Program, NKC, which consists of 9 Saturdays of approximately 6 hours of coding instruction each. And this includes playing Gidget, learning HTML and CSS, and getting experience with block programming through Scratch, following this official Scratch curriculum. We also include enrichment activities, including drone programming, learning about sorting algorithms and binary counting through VR apps, and things like that. And one important aspect of NKC is that it's taught entirely by first and second year college students. So these near-peer mentors are very close in age with our younger middle school student participants. And because the college students typically dorm on campus, they're all also Newark residents. So they have a lot to talk about. So unlike the previous 2 examples of systems such as tangible user interfaces or online games, our data collection in these cases were a bit different because it was more about the overall camp experience. So we collected data such as the children's interaction with their near-peer mentors. So for example, how many questions they asked, if they eat lunch together, game progress and project progress, pre and post questionnaires designed to measure attitudes towards computing and learning outcomes, daily end of day reflections, and semi-structured focused intergroup interviews. And as we did before, we use our data to make iterative improvements to the next day of the program and also the overall program itself. For example, we made many minor tweaks to the day's activities, making projects more personally meaningful to the young students. We've also trained a lot of in-service middle school and high school teachers who want to integrate more coding into their actual classroom activities. So we provide free professional development courses for K-12 teachers every summer. And next, the big question was sustainability and long-term effects on the children. We did not want this to be a one-time opportunity for the kids to code and them have nothing to do related to code until they go to college. So we teamed up with the Urban League and we launched Technology House, which is open to the public and located in central Newark or in a residential neighborhood. So a few simple overall takeaways to summarize the talk. So as you've seen, data can take many forms depending on the type of system or the project that you're working on, and the data metrics can provide information about system performance, but data can also help to change and inform the user experience, both directly and indirectly. So it can be helpful to the user more or less explicitly within the interactivity built into the system. So I think that's it, and that concludes my talk. So thank you very much for your attention, and I'll turn it back over to Kayla.
Awesome. Yeah, this is great. It was so great to see the kind of the different ways that you both kind of conceptualized and actionalized data in your work. One of the questions that I had is related to how you start to conceptualize what normal looks like for students, either through the processes that they're going through or the ways that they're interacting with the system. And kind of one of the things that struck me is this idea of what do learners think their purpose is when they're doing certain things, and how that might feed into your understanding of what maybe normal might look like. I don't know, whoever wants to.
Should I get that first, Matt?
Yeah, I'm happy to take that one first. So, thinking about the particular study that I was talking about, we were very lucky in that sense because we were, doing think aloud interviews where I was sitting down with a single individual solving those problems and talking aloud. So if anything kind of came up that was, confusing or I wasn't quite sure, what sense I might make of it, I would just ask them. And so, it helped me to kind of calibrate on what a sense of what a normal process was for that individual. Now, of course, that's a really different kind of thing than what you can do whenever you're talking about the scale of something like Gidget, as Mike was sharing, right? And I think there, I'm really curious to hear kind of Mike's answer, but my instinct with working with something very large like that would be to, of course, looking at averages, but then really digging into outliers and seeing if you can bring people in and kind of have more in-depth conversations with folks who, on various of the metrics you're looking at, ended up being outliers, because that can be really, really instructive in kind of understanding how people are using the system.
Mm-hmm.
Yeah, so for me, I think normal didn't really exist in any of these systems because different people use it so differently. And like Matt alluded to, there are definitely outliers, right? So there are big chunks of people who are very, very similar. And from that, we use the averages to make this frustration detector, for example. But we found that some people played one level and they quit, right? And that was kind of strange. And we hope that it wasn't because the game was no good. So we actually followed up because we had their email addresses. And a lot of times we found that these were actually teachers, right? And the teachers just wanted to come in, check out the game, and come back later with their students, right? So they wanted to kind of make sure that it was a system, because a lot of times schools, for example, block games from their computers, from their network. So they wanted to make sure from home that it would work. They check it at school, and then they sign up their whole school for it, right? Talking to outliers was really, really important because we wouldn't have known this, right? We just would have thought that people didn't like the game because they're quitting after 1 minute of playing the game, right? So I think it's really important to think about what your data means and try to get correct interpretations of that. But you should also follow up if you can with these individuals, right? Because aggregate data is useful in certain ways, but individual data is also really, really important, right? So when you say normal, I guess, sometimes we have things like Gidget where we have a set curricula. So it takes a normal path, but some people would probably like to deviate from that, right? So we do open up access, for example, to this open system where you can kind of just explore and create. And some people prefer that, right? And so they don't want to sit down and have this set curricula with stringent rules. They want to just explore, right? So depending on who your audience is, I guess defines what your normal would be.
Yeah, and I think one other just really quick point that Mike, your response made me think of is, as Kayla alluded at the very beginning, CS education is a very new space. We're all kind of building airplanes as we're flying them. And so I think even, for much more established fields like, I don't know, mathematics education, something like that, it may be a little easier to characterize what a normal is. And I think in CS education, as Mike was saying, everybody interacts with tools so differently and uses them for such different things. It's very difficult, I think, to even characterize what that idea of normal would be.
Yeah, for sure. If there's anybody in the audience that wants to ask a question, I don't want to capitalize the whole time, but I can also keep asking questions. But I guess kind of thinking about like this idea that we don't really know what normal is, or maybe like what the best approaches are and that kind of thing. When you're thinking about like the forms of data that you all have and the forms that you don't have, when you're trying to kind of get to, I think, Matt, what you were saying, this like kind of like unknown understanding that's existing in the head. How did you guys make decisions on like, yes, this process and like identifying, for example, in Matt and your work, like their iteration between them is the thing that probably is the most close to what I'm getting at or trying to get at?
Yeah, and I'm happy to go first if you don't mind, Mike. But I think, again, CS Ed being such a new field, the work that I was describing was explicitly exploratory, right? We weren't trying to say, oh, and we think this process is going to be a better one to result in a solution. We were just trying to say, okay, we're going to modify some things in the items, kind of hand them to some students, and then see, what sort of differences there are, if there were any. And I think I know in other domains, I'm thinking about like process research around natural language writing, right? Like essay writing. A lot of that work has shown that there's a variety of processes that result in sort of equally successful work. And so the way that's been operationalized, for example, on the National Assessment for Educational Progress, the score that an essay someone writes might be exactly the same, and you see really different processes, like somebody just sitting down and writing from as soon as they're allowed to, and kind of just writing the whole thing, hardly erasing anything. Other people waiting minutes and planning and then writing. And so I don't think there's enough research around to say this for certain about CS education, but I expect that we would find the same kind of variety in the sense that a lot of different processes are successful or result in a successful product.
To add on to it, I think I've had a very similar experience. So a lot of the work that we've done was very exploratory because there weren't any guidelines, but there's not much research with, for example, large-scale debugging games online, right? So what we did was took a very iterative and participatory approach, really thinking about inclusion as well. So we really tried to kind of incorporate many stakeholders' feedback from the beginning, release a version, and do iteration, right? So each of these studies that I talked about informed the next version, and the next version was, hopefully a little bit better than the previous version. And even for the data collection, at first we didn't know what we were missing, right? And we realized later, hey, we don't know why this is happening. We should ask a question about that, or we should somehow measure that, right? So we would add that to the next iteration, right? So this has been very, very exploratory. And I think now we are maturing a little bit more as a field. So now there are kind of more, not really set standards, but ways to kind of do things. And like Matt said, these different kinds of processes, maybe there's not one best way, but there are several ways. So I think, as a community, trying out these different ways and reporting on that is really, really important.
Awesome. And then Yoav, did you have a question?
Yeah, I'll follow up on what has been going on. First of all, thanks, Matt and Mike, for excellent talks. And in particular, I just wanted to say that apropos of Matt's talk, which is really up my alley, it's great to see someone, describing the sort of perspective of CS assessment where from an analytics perspective, we're like, okay, students could produce process data that we could analyze. But from a, validity of interpretation of test scores perspective, we want to know what it is that we want to claim about that. And so, if you say, hey, can you program here's a prompt, write a program. At the end of the day, some TA will score that program. You get 5 out of 5. And what you're driving at is, but there could be more information there about what the strengths and weaknesses of the student is, and what we could sort of provide as formative feedback to the student. And maybe we could even design the assessments better to tell us more. So apropos of, Kayla asked it in the language of, what is normal behavior? And I would just sort of, for the whole conversation, translate that from in the way I think a psychometrician might, which is what is expected behavior in response to a particular prompt. And we don't necessarily know what expected behavior is without experimenting a lot, which is how sort of test development works. You put prompts out there, you see what students do, you change the prompts, you see what students do. And this early exploratory work is all about that, which is awesome. So on the technical side, what I wanted to say and then ask is that when we do that in this exploratory way, we look at the sort of sequences, observed sequences, and then, you described various sort of sequence mining or distance metrics on comparing sequences. In my own experience, I've seen how sensitive the outcomes of the analysis can be to the choices of things like sequence distance. So you use a different sequence distance, you kind of get different breakdown of the difference between the open prompt and the closed prompt. And part of the problem there is that everything is sort of after the fact. Like, we haven't started with a theory of how do we elicit certain behaviors, and then we see, are we eliciting those behaviors? And if not, our prompts are bad, right? Throw the prompts away, start again. So what I want to hear from you, and then maybe Mike would have a different spin on this, is have you thought about that sort of forward vision, and think sort of blue sky, if you can, about how we could really design for eliciting the complex behaviors that we might expect in order to be able to make those sort of diagnostically deep inferences that could be formatively useful?
Yeah, thanks for all of that. There's a lot of interesting parts of your question there. I will say that you're right. So like I chose longest common subsequence because I had sequences of different length, right? And so that was a really good metric for that particular instance. It was also a very low sample size. So, it's unlikely, I think, the case that I would find exactly the same sort of thing in another population or with another set of students. And I think, to me, what it calls for is that what's one of the things that's missing in CS education is a real theory, right? Of this is what kind of a developmental trajectory looks like as someone goes from a non-programmer or a novice programmer all the way through to whatever, however we would characterize expert performance in that domain. And because that theory is missing, you're absolutely right. It's hard to kind of connect what we're observing on a micro or even on a more macro level with kind of what we would expect someone's progression to be over time. To develop that, I think one of the really interesting things about CS education as a space is oftentimes people are creating the thing that we want to assess on a platform that's easy to instrument, right? So we can get all sorts of process kind of data. And to me, the way forward seems to be this kind of iterative back and forth between like, well, let's try this bucket of process data. Do we see anything interesting? And then using that to feed into some more perhaps qualitative kind of work where, we're actually sitting down with students and seeing, does that thing that we found in this big bucket of process data that seems to be connected to expert performance, is that actually how students are operating? Is that actually the understanding that they need to bring to this item in order to solve it? So I'm thinking, for example, like some of the work that's been done with the PISA complex problem solving items, right? There's a very clear theory of varying one thing at a time, right? As the correct systematic approach to solving the item. We don't have anything like that, even for the simplest program that we might ask someone to write in CS education. And so to me, the way to get that is, again, to really just think about what's that developmental trajectory, what are the understandings, the knowledge, skills, and judgments maybe that someone has to learn, to know, and to make as they learn in that domain.
So I don't think I have a specific answer to the main question, but talking about measurements and students' understanding, that just got me thinking about some of the things that I've seen, especially with Gidget, especially prototyping earlier versions of it. where we had students or just random people, different stakeholders, come and play the game without being told that it was programming or debugging. So it was just a puzzle game that they were playing. And for the people that we said, just here, do this other task, we were testing for transfer, they would, for the most part, do well. They'll be able to do the task and show transfer and knowledge, right? So that's good. But then for the people who we said, hey, you know what you're doing is programming, they'd be very surprised and they would kind of shut down and they wouldn't be able to do the task because we got comments like, oh, I didn't know what I was doing was programming. If I knew it was programming, I wouldn't have gotten so far. I wouldn't have been able to do it, right? But I would say things like, hey, well, but you got to, you completed half the levels. You do know how to do it. But this kind of self-efficacy and these preconceived notions about programming and their ability or their inability to do it would be a big deterrent. So I found even in cases where they would probably be able to perform well, these other factors, these other confounds prevent them from doing well. So I think in our measurements, we also have to kind of think about these other things that may be happening. And this would also be important, especially for increasing participation and diversity in computing. These things are, I think, essential to kind of know about more.
Awesome. Thanks so much. So it looks like we have a chat question from Riley. If you want to come off mute and ask.
Hi, can everyone hear me? Thank you. Yeah, so I just wanted to ask, and this is like a really, really big question you can think about for a long time, but I guess how the implementation of both of your ideas kind of pans out, or how they engage differently for older secondary school students versus younger primary school students. Just because I know there is background noise, I'm so sorry. I'm in a public space. Because I know that, for example, older students love to advocate, for themselves and talk about their data and how good the test was at measuring, but how do younger students engage in, that empowering of their own data, analysis of their own data, and then maybe for game design aspect, for Gidget, and for learning and any other traditionally more novice languages like Scratch, how do older students engage with that? Because I definitely think they're critical enough to think, to ask those questions of how is this programming that, younger students might not want to ask. And maybe you can kind of relate to that, to your experience, Michael, of, those students that you were working with in that community, because I know they were a little bit older. So big question. Hope that makes sense.
Yeah, I think that's a really, really interesting and good question. So as far as working with younger children, they have different abilities. So, with an adult, someone who's 18 years old, who's in college, you have a specific idea about what their abilities would be. But for younger children, especially, if they're 4 to 6 or 6 to 8, they have very, very different abilities, right? So designing for them is a big challenge. And I think thinking about who you want as a target demographic, and thinking about that really early is key in the design, because if you're going to design something for younger kids, you should stick to that, because some of the things that may work for really young kids may not be appealing to older people, right? But some things may be. So for example, the Gidget game, it's intentionally cartoonish, looks easy, looks cute, because people then think that even though this debugging puzzle is hard, that there must be a solution. So I'm going to complete it, right? It's a game. There must be a solution. Even though it's hard, I like puzzles, so I'm going to do it. But if you just give them the debugging task, they're not going to enjoy doing that, right? For the younger students, actually for all students, we found that having them included in the design process was very empowering, regardless of age. So if they would say, hey, I didn't understand this icon, or I didn't understand what this did, and in the next iteration, they came back in and we had changed it according to their feedback, they would love it, right? And even telling other children who didn't participate in design and saying, your peers, people of the same age as you, helped in the design of this, they also felt empowered, and they were more likely to, say that they liked it, they enjoyed it, and were much more engaged in it, because they felt that their voice or peers' voices were heard, right? As far as interactions with Scratch, so I've had many different experiences. So young children nowadays are exposed to Scratch very, very early. And so sometimes older kids, they have seen it, they've either used it or they've seen it. So some of them may feel that, hey, it's like a kid's language, right? But I think the more important thing is to get them engaged right? So whether it be Scratch, whether it be a textual based language, getting them engaged is the key thing, right? So one of the design decisions we made early on for Gidget was to implement a programming language, right? A text-based imperative language, because we wanted that transition from a game to like Python to be as seamless as possible. And newer versions of Gidget are going to include, the ability for people to kind of choose the language they want to do. So like kind of plug and play. So you plug and play JavaScript, Python, block programming languages. So you can kind of choose what you want. And I believe, by giving different people choices, it empowers them, increases their self-efficacy. So, you can get a larger breadth of people to participate, which again, I think is important. So allowing people the freedom of choice, I think that is also helpful.
Awesome. Thanks so much. So we are a little over time. So I just wanted to thank Matt and Michael again. Your talks were amazing. And hopefully we'll continue to see you in the Learn community. And thanks everybody for joining.